Hello everyone and welcome to today's webinar, Active Traffic Management Implementation and Operations Guidance. Before we get started, I would like to go over a few items so you know how to participate in today's webinar. First, a quick intro about the webinar host. The National Operations Center of Excellence, or NOCO, is designed to offer resources for transportation systems management and operations for TISMO community. We have a variety of technical services such as peer exchange workshops, webinars, and ongoing assessment of best practices in the field. Feel free to browse our entire collection of NOCO resources in the Knowledge Center. I'll share the link with you later in the chat box. So a recorded version of this webinar along with the presentation slides will be available for access on our website within 24 to 48 hours. To access this, come back to our website, go to the Knowledge Center, and choose the On-Demand Learning tab. I will share the link in the chat box again. For those of you just joining us, welcome. We are about to start today's webinar on active traffic management. With that, I'll hand it over to Bill.
Good morning, good afternoon. Let me be moving this slide here. Milo, did you hand it over?
Yes.
Okay.
Just click on it.
Okay. So just go over a few housekeeping items, introductions, and then we'll get to the meat of the presentation, overview of the active transportation demand management, the guide, and an ATM implementation example, and then questions and answers at the end. So please, everyone's phone line's muted during the webinar. If you have questions, enter the questions in the question pane anytime during the presentation. And as I said, we'll come back to those after the presentations are over. Contact information for the presenters will be provided at the conclusion of the webinar. And this webinar was developed as part of a project funded by Federal Highway Administration. As I said, my name is Bill Perez. I'm the program manager of that contract for Patel. And we thank the National Operations Center of Excellence for hosting today's event. And again, thank you, all you participants, for being here today, this morning, or this afternoon. Our speakers today will be James Collier from Federal Highway Administration, Office of Operations, Beverly Kuhn from Texas A&M Transportation Institute, and Vin Dan from Washington State Department of Transportation. With that, I'd like to turn this over to James Collier. James?
All right, thank you, Bill, and thanks for the introduction. And today's webinar is really going to be focused around a recently developed guidance document that Federal Highway has developed on active traffic management and implementation and operations. And so we're going to share a few things today. One is kind of the context of this guidance and how it can be used and where it can be used by agencies to help them in their decision-making processes of implementation and operating their ATM systems. Also give a quick overview of ATM concepts and strategies if you're not familiar with them. Going to talk through the guidance documents and kind of the chapters of it and cover at a high level some of the critical issues and best practices and lessons learned that are in the guidance. And then finally, we'll wrap it up with Vin from Washington State DOT that will give his experiences from their ATM deployments in Washington State and the Seattle metro area. And I should say this guidance document is going through the final review process right now, so it's not currently publicly available, but it should be shortly, and I'll give a link at the very end of the webinar where that will be posted. Okay, so I'll give a brief overview of ATDM, what it is, and you may have heard of the acronym ATDM and wondered what's the difference between ATDM and ATM, and so I'll just give a quick intro at a high level here. So ATDM, it really has an underpinning of active management cycle, and as you see the graphic here, it really talks about the concept of managing the system in real time through a series of functions that are a performance-based feedback loop. So you're continuously monitoring the system, and that feeds to assessing the state of the system at any point in time. And based on that assessment, you can have the capability to evaluate and recommend dynamic actions. The implementation of those actions results in improved system performance, which then is fed back into part of the monitoring function. And with the active management cycle philosophy, this is really all done in real time. So the goal of ATDM is really to attain the capability to dynamically, and dynamic is a key word here, monitor, control, and influence travel, traffic, and facility demand of the entire transportation system over a traveler's entire trip chain. And so as you can see, ATDM as an overall concept is fairly holistic and pretty broad in terms of its application areas. And when we talk about trip chain, we can think of it as every trip on the system has an origin and destination, and there's a number of decisions that travelers have to make, whether or not they're consciously aware of it or not, but they're deciding where to go, what time to leave, what mode to take, which route to take, and then finally which lane or facility to take. And so all of these decisions fall under the purview of ATDM in the fact that we can influence or control the performance of each one of these choices that travelers have, and giving them real-time information so that they can make good choices for themselves, and in the end will improve the performance of the entire system. So another way to think of ATDM is it has three broad buckets. One is demand management, active demand management, where it's more than just a traditional like carpool program or traditional demand management program, but it's more of a dynamic, fluid process of incentivizing and influencing travelers' demand decisions. ATM, which is the focus of today's webinar, active traffic management, and maybe a little bit more prevalent in terms of what people might be familiar with. But here we're talking about traffic management strategies of dynamic speed limits, dynamic shoulder use, dynamic lane assignment, and others. And then finally, not to forget active parking management, which is an important part of travelers' decision making and route and mode choice, in terms of, especially in urban areas as well. So we have parking pricing, real-time parking availability, and reservation systems. And so some of the things we'll talk about today under ATM, some of the examples are maybe more of an urban area or freeway-centric, but just want to make the point that the ATDM and ATM specifically can be applied in really any setting, urban or rural setting, and it can be applied not only on freeways, but arterials and any other kind of multimodal transportation system as well. So Federal Highways had an ATDM program for like the last 6 or 7 years, and just trying to increase awareness and understanding of ATDM concepts and strategies, developing and evaluating different strategies, or providing different tools and methodologies for performance analyses and benefit cost analyses, and also finally training agencies to deploy effective ATDM systems. And so this guidance document we're talking about today falls and is funded through Federal Highways ATDM program. And with that brief overview, I will now turn it over to Beverly to talk specifically about the ATM implementation and operations guidance.
All right, thank you very much, James. Good morning and good afternoon, everyone. For about the next half hour, I'm going to go through the guidance that was developed as part of this project at a very high level. As James indicated, the document's not quite ready for prime time, but will be available soon. And we look forward to giving you this opportunity to find out what's in the document and how it can help you in your daily activities with respect to ATM. What I'm going to briefly go over in the next few moments is the team that put together this document, go over the project objectives and activities and what was done by the contract team to provide this document. We'll discuss the guide itself within and the objectives intended for that particular guide, and then give you an overview of the individual chapters and a snapshot of some of the content that's included. And then we'll turn it over to our expert from Washington State so you can hear about their experiences. The FHWA team was made up of James Collier, who was the contract manager, Jim Hunt, Jimmy Chu, and Greg Jones. And they oversaw the project from the Federal Highway Administration side of things. Bill Perez, who you heard speak earlier in the presentation with Battelle, was the project manager for the contract, and then I was the lead from the TTI side, as well as my colleagues Nick Wood, Kevin Balke, and Jerry Ullman, and we together pulled the material together for this guidebook. We also had the benefit of an external advisory panel, and the members of the panel that participated throughout the project are listed here. You will get to hear from Ben Dong, who with Washington State, and he's going to provide some information on their experiences in Washington, and they were a very valuable asset to the project and gave us insight from their experiences, which led to additional content and resources for the project. The objective of this project was to produce a guide for agencies of all sizes who are either interested in implementing ATM for their region and haven't done so yet, but they're considering it, as well as agencies that have implemented ATM already and are interested in how to operate their systems better, or to enhance strategies that they've already deployed or add to the ones that they've deployed to better optimize their system. Throughout the project, we investigated current and best practices, lessons learned, future trends, what has gone on in the United States to date with respect to ATM, and where there are experiences that we can capitalize upon to include in the guide. We prepared the draft, and we're in the final versions of the guide, focusing on implementation and operations, and that's important because there are other resources that are available specific to earlier aspects of developing an ATM project, and then specific strategies, but this focused on all the ATM strategies, but only within the implementation and operations perspective. We also prepared an informational brief to create broad awareness of the guide, which will be available soon on the US DOT website, and then the final activity is to prepare and conduct this webinar. So if you're familiar with the content of, or the concept of ATM, you've heard about it over the last, say, 10 years, and there's a lot of information that's out there, and so what we first did was identify the context of this particular document. And as you can see, the scope of ATM ranges from single strategy resources, say you just want to deploy ramp metering, to the multi-strategy resources like what you're going to hear from Vin about in Washington State, where it's a broader multi-strategy deployment, which involves different aspects. In terms of the phase of a project, it goes from planning to operations and maintenance. So we focused on the multi-strategy approaches primarily from that implementation and operations side. So that's this yellow arrow here that you see. These highlights here are other documents that are available, the guidelines for variable speed limits in wet weather, the ATM feasibility and screening guide is currently available. This NCHRP document is in final development. The use of freeway shoulders for travel is an FHWA document that's available, and there's some ramp metering resources as well. So this is where the ATM guide that we're going to talk about fits within the context of all this ongoing activity and resources associated with ATM. The guide has two primary objectives, which I did discuss earlier, to enable agencies to make informed and sound decisions regarding implementing and operating their systems, and deciding what strategies are appropriate for their region. And then for agencies that have already implemented ATM, it's intended to provide them with resources about how to better operate their system, to incorporate strategies that they might already not have in place already, and just how to make it more effective for what its intended objectives are. We wanted to highlight best practices and lessons learned, provide insight into what might work for your region. The guidelines are not intended to focus on how to plan for it, but really once you have the system designed, how you're going to implement and operate it effectively. In terms of the use of the guide, it can be used to implement ATM in a region to operate them more effectively if you already have some systems. It's also can be used to help incorporate ATM into your overall transportation systems management and operation program. How does ATM become part of your part and parcel of what you do with your system and make your system more effective? It's just a tool in the toolbox and making sure that it's part of that program. And then also to highlight the potential benefits for these types of strategies and determine how these strategies can help meet the overall TSMO goals and objectives that you've established for your region, and how you should incorporate them into your strategies to better meet the needs of your consumers. The guide has 7 chapters, and we're going to go over we're going to go through all of these in some level of detail. It's broken down into just an overall introduction to ATM. We also provide information on planning and organizational considerations. This ties back to the capability maturity model and capability maturity framework to make sure that your agency is organized such that it can implement these strategies and operate them effectively. We're going to talk about design, implementation and deployment, operations and maintenance, and then we have some final remarks looking towards the future and what it holds for ATM. So chapter 1 is the introduction. These are the subsections that are included in it, the goals and intent and the audience. And these are the strategies that are incorporated in this document. And they're listed here: adaptive ramp metering, adaptive traffic signal control, dynamic junction control, dynamic lane reversal, dynamic lane use control, dynamic shoulder lane, queue warning, dynamic speed limits, and dynamic merge control. And those all fall under the active traffic management umbrella. And we'll go into a little detail into what's included in all of those. An early adopter is Washington State. That's who you're going to hear from later on during this webinar. They've had 3 deployments in Seattle thus far, and they've branded the ATM concept Smarter Highways. 2 components of their ATM deployments involve variable speed limits and dynamic lane use control, and you can see here a sign on the right, a photograph on the right-hand side of the deployment along I-5. Another early adopter in the rural application is Wyoming. Along I-80 between Laramie and Rawlins, the Wyoming DOT had severe weather events and high winds that were creating closures that generated congestion along that route, and so they deployed variable speed limits along this route to help mitigate some of the situations associated with the weather. So they could reduce speeds in response to road conditions, wind surface, and atmospheric conditions to hopefully offset the impacts of the bad weather and reduce the likelihood of crashes. For each of the strategies that we've discussed in that earlier diagram, the document includes a number of items. It includes a name and also different names by which that strategy might be known. An example would be dynamic shoulder use. It might also be thought of or heard of as hard shoulder running, dynamic shoulder management. There's lots of different strategies, terms for that. So we wanted to include all of those so the reader understood what that strategy encompassed. We have an acronym for it, which is used consistently throughout the document to make things a little easier to read, and we provided a definition for that strategy and what it means. We also provide information about the operational scenarios under which you would deploy that strategy. For instance, does it work well with recurring congestion? Can you use it in a work zone? Is it something that can be deployed in response to incidents or some other strategy like that? And then we provide information on an application geography. Is it a strategy that's appropriate for a limited access facility, an arterial, or an interchange and a ramp? Just so the reader has an opportunity to clearly pinpoint what works best for what their challenges are. And then we provide examples of where these strategies has been deployed in this chapter and any links to resources located elsewhere that are good documents to review with respect to that strategy, so the reader has other resources to provide. We did not want to make this document duplicate efforts that had already gone on, as we indicated earlier, so those links are pretty critical within the document. We do give there is a link between ATDM and ATM, as James mentioned, and TSMO. And ATDM incorporates those strategy categories, as James discussed earlier, part of the active management cycle. And ATDM falls within the overall TSMO mission to have strategies that are dynamic, predictive, proactive, performance-driven, continuously monitored, and help balance the supply and the demand on the system and fit within an overall TSMO program. The systems engineering approach is also very critical to successful implementation and operations of an ATM strategy. This is the traditional systems engineering diagram that I'm sure most of you have seen in the past. It is a logical approach to implementing these strategies. It just involves a little additional technology associated with it, but it's very similar and it's very applicable in this realm. So that's the highlights of Chapter 1. Chapter 2 takes us down the planning and organizational considerations discussion. So these are the different sections that are included in the chapter, and I'm going to give you a little highlight to that. One of the things that's very important to reflect on is that the development of ATM strategies is part of the objectives-driven, performance-based approach. This approach is reflected in a lot of material on the US DOT website, but it looks at identifying regional goals for your system, identifying what your operations objectives are for the network, and establishing performance measures. What are those performance measures that you want to use to determine whether or not you're successful at your operations objectives and meeting your goals? Management and operations strategies flow from those performance measures, and that is where ATM comes into play. Operation and ATM strategies fit into that TSMO umbrella, and this is where it becomes part of the performance-based approach. Investment and implementation in those strategies makes them a reality, and then the monitoring and evaluation of ongoing monitoring and evaluation helps the agencies determine whether or not the ATM strategies that they've deployed are helping them meet their regional goals and objectives. It's part of that active management approach that we've shared earlier, and it's part of this broader approach as well. And that's where ATM fits into this management approach. Another aspect that's important to consider from an agency perspective is whether or not there's organizational capability that can support ATM operations. Organizational capability falls into one of 4 levels or somewhere along the spectrum, and it goes from operational strategies. Is the organization have a champion in-house that's promoting ATM? As ATM becomes more part and parcel of what an agency's doing and part of their decision-making processes and their organizational mission, then ATM becomes part of the conversation. It's part of the TSMO solution. And optimized level 4 looks at making sure that the agency has performance-based improvement as part of their processes. They have a formal program that considers ATM throughout their activities, and they have formal partnerships to make this a reality. This is very similar to the 4 levels that you will see in the capability maturity model and the traffic management capability maturity frameworks and some other resources that are available on the US DOT website. And it's all focused around making sure that an agency has the business processes, the systems and technology, the collaboration, the culture, their performance measurement, and other capabilities in place so that when they deploy ATM, they're successful at it. One of the most important aspects when determining what ATM strategies to deploy is to set the objectives and performance measures for those. We provided information on what objectives and performance measures are practical for each of these strategies and focus on the fact that those objectives need to be SMART, specific, measurable, attainable, realistic, and time-bound. We also provide resources on travel time reliability, as that becomes, that concept is becoming more and more important in providing mobility for system users. We provide information on congestion management objectives, safety objectives and performance measures, as well as those that get at sustainability and livability for the system users. Additional planning, the document provides information on analysis, modeling, and simulation. So before an agency decides it wants to go down this path, they can do some modeling, some assessment to determine what they can expect in terms of mobility benefits of the strategies, what likely safety benefits might come out of this strategy, and what are the benefits and costs. Is it going to benefit the community in the way that they would like it to at a reasonable cost? There's also some guidance on programming and budgeting and how to incorporate ATM strategies and ATM concepts into the overall planning and budgeting programmatic activities so that it can compete on an equal playing field with capacity improvements. Chapter 3 looks at design considerations and what are the key elements associated with that as an agency moves forward with designing a system. The first step is developing a concept of operations. The ConOps is, for any large ITS project or any large infrastructure project, is not a new concept. It fits nicely. It's going to be required for an ATM strategy, and these are the elements that need to be included with respect to a ConOps for an ATM project. Some of the things that are very important associated with developing the ConOps with an ATM strategy is those operational needs. Since these are dynamic in nature, it could require additional technology and understanding how the system is going to operate and how you're going to monitor it and adapt strategies over time or in real time to optimize performance. A lot of that is tied to your performance measures. What are the real-time operational strategies that you want to deploy? What combination of strategies are you going to deploy? Under what scenarios are you going to deploy them with respect to an incident, weather events, planned special events? Are they going to be used for work zones? In similar scenarios. So that all needs to be built into the concept of operations. It's more complex than a more traditional strategy because it is dynamic in nature and there's lots of variations in how the strategies can be deployed depending on the scenarios. The requirements associated with the ConOps are extremely detailed, especially with respect to the technology associated with it. And these are the typical requirements that would need to go into that document. What are the requirements for the system, verification methods for those requirements. Once the system goes online, are you going to be able to verify that it's accomplishing what its original intent was, supporting documentation, terms, acronyms, and definitions. And the more strategies you incorporate into your ConOps document, the more complex the requirements become, especially as they start to integrate with one another, and if you're going to deploy variable speed limits along with dynamic shoulder use, and you have lane control signals, lots of things start to get very complex. The design elements for an ATM system fall into two categories. Those are the hard civil design elements, the things that are bread and butter of the traffic engineering design, the control devices, the geometrics. There is the consideration of emergency pull-offs when you're deciding whether or not you want to deploy variables dynamic shoulder use. The intent is, if you have dynamic shoulder applications in operation, the shoulder has now been removed from use for breakdowns. So how do you handle that? The decision to deploy emergency or to construct emergency pull-offs every half mile to mile or so on along the corridor is a design element that typically you might not necessarily incorporate into a traditional capacity improvement project. Associated with that is also some of the geometrics and some of the pavement surface design issues associated with shoulder running, for example. So if you're going to design a shoulder running, you need to make sure that you have accommodated for any pavement wear and tear. If it's a retrofit and the shoulder currently doesn't handle traffic, you need to make sure that it can handle the traffic that you're going to allow to use it. Do you have drainage inlets that you need to address? Do you have rumble strips or rumble stripes on that shoulder, and how do you accommodate for those or mitigate them? And then you also have the clear zone is impacted if you have if you're going to open up the shoulder. So these are all different. If you're going to open the shoulder and other strategies, what are kind of the big picture? What are the things you need to consider? Traffic control devices are also very important. As these strategies are fairly new to system users, you need to make sure that they understand what you're asking them to do and what's going on along the corridor. Are you there's lots of different aspects of using traffic control devices, different ways to convey the information to the system users. Could be lane control signals. You could use a traditional dynamic message sign. Static signs might be important as well. And what are the different ways that you're going to incorporate that information into the system without overloading the system? Because you do have an existing sign system already in place. So you're already providing information about speed limits and lane use to some regard along the corridor. So how do you supplement that or replace it depending on what you want to do in the corridor without overloading your system, your users? The technology elements are equally important. As we've mentioned throughout this presentation, these are dynamic in nature and involve a lot of technology in the field. It's not only the detection of the vehicles that are out on the system. You might need to use closed caption television if you're going to use open up shoulders for travel, because you need to make sure that that shoulder is clear before you open it up. And how are you going to determine that shoulder is clear? Through cameras. You're going to have somebody drive along that shoulder before you open it up. There's different ways to do that. Well, that's a new technology that you may have to deploy in a corridor. Communications is important. If you have electronic signals as sign systems out in the field, dynamic message signs, beacons, lane control signals, those all require technology and communications to interface with your existing traffic management center. And then there's the software and the controllers that run your ramp signals and your lane control signals. And that software with the algorithms running back in your TMC is very important, and that is an element that you cannot overlook. Let's see, there we go. Infrastructure design. I've already mentioned some of this. Shoulder pavement, fixed objects, vertical clearance is important as well. These are all different elements that need to be considered when you design the system. There may also be an occasion where you have to request a design exception, and there is a process associated with that FHWA has information on that you would need to follow. If you're going to use signs that don't currently exist in the Manual on Uniform Traffic Control Devices, there's a process for requesting approval to experiment with signs that you, if you're going to be using something that's not in the MUTCD. The ITS design, as I mentioned earlier, can be very complex. This is a screenshot of what's being used in Washington State, and it involves hardware, connectivity, a lot of data, software design and integration. There's always the decision with that software, is it something you're going to design in-house and maintain in-house, or you're going to contract that out? And that's part of the decision process and the design and implementation of it. Vin may go into some of the details with this system, but as you can see on the left-hand side of this diagram, those are camera feeds. It shows shots of the facility where the ATM is deployed, and then they have some user interfaces that illustrate what's going on in the field right now and what the variable speed limits are showing, and so the operator in the TMC has a quick snapshot of what's going on in the system. They can also do some offline scenario building to see what's the most appropriate strategy to deploy at a particular time, and it looks very similar to this. Procurement and testing can be very complicated or tricky associated with the technology that's being deployed. There's the software delivery model that needs to be considered, and then there's also the testing of the equipment. The photographs here in this slide are ones from Seattle, where the signs that are used were tested in the field to determine whether or not they were working appropriately and delivered the messages that were necessary. And they just had a testing facility where they ran the signs through their paces to make sure they would accomplish what they needed to do. Maintenance becomes an issue as well with some of these signs, because it's a new thing, and your technicians may need to be trained on how to maintain these signs. If they're over the lane, that does impact maintenance activities and whether or not you need a lane closure. So there's trade-offs associated with doing a sign bridge that goes all the way across the facility as opposed to just a shoulder-mounted sign. And how easy this technology is to replace, and what to do with legacy systems. Here are some procurement lessons learned that came from some of the sites that have deployed ATM, that it does require more precision and skill to implement these than some more traditional strategies. The signs that you're going to deploy need to be durable and of very high quality. You're expecting a lot of those signs. And it should supplement, ATM should supplement your ongoing traffic management activities. It's very important through the procurement process to have continuous communication between the managers and the software developers, so that the software is going to, the end product is going to accomplish what is intended for the system. And there are some other factors associated with a traceability matrix to make sure that the process has been followed appropriately, and if looking at design build procurement documents as well. So there are different resources available and examples about that the reader can use to look at what's the best approach for them with respect to procuring their system. Chapter 4 looks at implementation and deployment. And construction and scheduling is one of the sections that we provide in the document. And there's a lot of different ways, as with all transportation projects, there are different ways to approach developing and constructing these systems. You could do a design build contract, a design bid build a contract, construction management at risk. A public-private partnership might also work as well. There are advantages and disadvantages to all of these, which we outline in the document. Through all of them, coordination and scheduling are very important. You need to make sure that the agency is closely involved in the entire process, and so that as equipment is procured and systems go online, that everything's coordinated, so you don't have equipment that's sitting in in a warehouse for months and months on end because it's ordered too soon, and then hopefully make sure that you have plans in place for redundancy if you have systems that fail or you have equipment that needs to be replaced. How do you deal with all of that? And then the schedule as well is very important so that you don't fall behind. There are some legal issues that need to be addressed at some point throughout the process, hopefully before you go live. The legality of some of these strategies needs to be researched. I will say in some parts of the country, shoulder use for all vehicles is not allowed. And so in other states, dynamic speed limits have their own idiosyncrasies when it comes to the state legislation. So if those roadblocks are out there, they need to be resolved before you head down this path of deploying these types of strategies. Enforcement is another issue that needs to be addressed early on before your system becomes operational. That means getting local law enforcement perhaps involved in the beginning to explain to them what the strategy is going to entail and working with them to help identify an enforcement strategy if, say, you want to enforce dynamic speed limits as opposed to having them dynamic speed advisories. That's a local choice. We have examples of both, and depending on how it's deployed, both can be effective. But if enforcement is going to be involved in a strategy, you need to make sure that law enforcement is in the conversation early and often so that they don't get blindsided when the system goes live. There are important policies to look at in terms of validation of the system, working with your operators to make sure that you have policies and procedures in place so that when the system goes live, you know how to manage it, and the operator's prepared for different scenarios that might occur. There might also be a need for additional staffing or equipment, and how are you going to handle that? How are you going to budget for that? What is that going to entail? And planning, the earlier you plan for all of these, the better. Throughout the entire process, stakeholder engagement and outreach is very important. I think some of the most resonant lessons that we have heard from implementing agencies is engaging your public, conducting ongoing outreach, not only building up to the deployment of the system, but into operations is very important, and involving the public all along the way helps make the deployment go smoothly. Identifying those stakeholders early and involving them in the team makes things function much better when it's all operational. There's a lot of different ways to disseminate information to the public and to your system users about how the strategies are going to operate, and you can share successes. There are different ways that agencies have deployed this information and shared it with the public that resonate with them. So here are some examples. YouTube videos of your simulation models that show the renderings of what the system's going to look like and doing a flyover so the driver knows what to expect. Brochures. The one here in the middle is a brochure that's been used in Highways England to much success, just educating the public on what the red X means and what they're supposed to do when they see that red X. And then Washington State DOT has an entire website devoted to their active traffic and demand management system, their smarter highway system, including videos and brochures and presentations. So there's a lot of ways to communicate early and often with your public to ensure that they understand what's going to happen when the system goes live. Chapter 5 covers operations and maintenance, and these are the different sections that are included. I'm going to go over some of them. Understanding your performance monitoring and how it fits in with thresholds is very important. As we've mentioned earlier, it's an active management process. Some of these systems can be automated. You can have a manual system where an operator makes a decision whether or not to open a shoulder or whether or not to change the speed limits, or you can have a hybrid of those. So making that decision before you implement is how you're going to manage the system on the fly while it's live is very important. And when you do that, you need to work to set thresholds for different strategies and identify what data sets are going to be necessary to calculate the information, the data, to see if you've met those thresholds, such as volumes or speed. So those are the kinds of things that you're going to look at. We provided typical measures for performance monitoring for each strategy, and the performance monitoring is very important to drive that active management in that cycle. So you look at it to make sure it's operating appropriately and tweak the operations. Performance evaluation just looks at the longer-term evaluation rather than the ongoing monitoring on a day-to-day basis. And this ties to the overall success of meeting your regional goals and goals and objectives. You want to collect that performance data over time to determine what the overall benefits of a strategy are, and whether or not you're meeting those performance goals that you set for the region. And data, again, is very important. Maintenance is very critical to the success of these strategies, as with all strategies that are driven by ITS technologies. You need to understand what the components of your system are, your field equipment, your equipment in the TMC, your detection, supporting signage. All of those elements are very important to understand what the cost range is. Is a strategy a moderate cost versus a very expensive cost, depending on how you're going to deploy it, and how often you might need to replace field equipment, having redundant systems, having backup equipment. What happens when the manufacturer of your particular piece of equipment goes out of business? Then what do you do if you have a legacy system and you can't afford to replace it immediately? Do you stockpile replacement parts to get you through until such time that it starts to fail, and then you want to replace it as part of your ongoing maintenance? So there's a lot of issues to consider there in maintenance. Incident management and enforcement are also ways, operational strategies that you need to consider when in handling these technologies. How are you going to handle incidents? Are you going to use the shoulder during the incident management? So say if the shoulder's open, you close it so your emergency services can access an incident. Do you open it to alleviate congestion? Do you station tow trucks? Do you have service patrols? There's lots of different components that you might consider. If some of these are already in place along the corridor where you're going to deploy these strategies, then they may not be anything new that you need to add, or you may just need to have some different scenarios for these these management activities in the event of incidents. Again, as I mentioned earlier, enforcement's important. Engaging the law enforcement in the process early is very important. And then if you're going to have the facility in the strategy enforceable, do you have support for the judicial system? Costs, we touch on costs in terms of the different funding programs where agencies can access resources to provide, to pay for some of these strategies. There's lots of different ways to incorporate them into your capital projects, as with other ITS systems, and just a lot of components that you can include. Some of the strategies are more expensive than others. One thing that I do want to point out is that you don't have to, some of these strategies can be deployed in a less expensive way depending on the needs of your region, and you can still be effective, sort of ITS light. The final chapter that includes information on impact of connected and automated vehicles and how you can use this guide as a transportation agency. The big question is, how are CV and AV going to impact ATM strategies in the future? These technologies can provide data to support your operational strategies in the interim before, between now and when all vehicles are automated and perhaps these strategies aren't needed anymore. a successful demonstration has taken place. It was funded by the Federal Highway Administration to look at providing ATM messages such as queue warning and speed harmonization into the vehicle, what would be expected from a connected vehicle or an automated vehicle. So that technology has been proven that it can be done. There have been some simulation activities that have been undertaken to look at dynamic speed harmonization and queue warning and how they do have a positive impact on system operations and the importance of data and how it impacts your algorithms. So the more connected and automated vehicles we have in the system as time goes on, they become a data point that helps make the algorithms more robust and helps the system be more responsive to what's going on in the field. So they play a role in how ATM will operate in the future. Exactly how remains to be seen, but it will work, and we know that they can be relied upon to provide data. So that, in a nutshell, not so much of a nutshell, is the contents of the guide. And right now, I'm going to turn it over to Vin and with Washington State DOT to talk about their experience with ATM in the Seattle region. Vin?
Thank you, Beverly. Let me advance to the next slide. Okay. So the concept of traffic management has been around with us for a long time. And in the next few slides, I'm going to go through how we grow with time and we mature. So back in the early 60s, we already had ram metering, and we have reversible facility to deal with the directional flow on I-5 as well as I-90. And one good thing is that during those early deployment of reversible, we already introduced the red X, and the green arrow is a lane control sign. So driver in this area is kind of familiar with those lane control signs already. And let me see if I can advance to the next slide. Okay, I'm sorry. Okay, and then following that early deployment, in the next 25 years following that, we install more infrastructure, and we also have additional program and initiative to enhance the capacity of the system, and mainly is the fiber optic communication backbone was being built as part of the I-90 completion, and then along with that, we also increase incident response program, and also at the same time we start using the RAM shoulder as the meter the storage for meter operation. So and then in the early 2000s is when we venture further into being responsive management. First thing we start also is the variable speed limit on in the rural area, responding to weather, and it was on I-90. And then a few years later, after that, we have VSL system, variable speed limit system on US2 as well. And during those times, we also enhanced the ram metering algorithm from the local bottleneck to the fuzzy logic, where we actually look at multiple locations along the corridor to come up with ram metering rate for any particular entrance, ram entrance. And also during this time here, we start the congestion pricing as a pilot project on SI-167, and that's kind of beginning of the congestion pricing era that later on will expand further into other routes. TMC also expand the hour during those times. So in 2010 is when we fully mature into what we call a proactive management, and during this time here, we start the full ATM project on I-5, and this system was turned on in October of 2010. It has pretty much all of the strategy that we can think of at that time: skew warning, the speed transitioning or speed harmonization, and junction warning, as well as lane control signaling. And then also during this time here, we automate the RAM metering turn on and turn off based on the occupancy in the corridor. And then also during this time here, we also introduced the remote or the automated operation of the express lane on I-5, and the remote operation of the express lane actually help us tremendously in terms of minimize the exposure of maintenance personnel on the roadway, as well as speed up the reversal process. And we also get involved more and more with the ITCM, Integrated Corridor Management Strategy, with the City of Seattle, with Bellevue, in terms of trying to manage traffic in the corridor along the arterial as well as the freeway in the corridor. And we also expand the congestion pricing more onto other routes. The SR520 bridge crossing is a toll point. SR16, same thing. The other difference is that on the I-5 express toll, the price is per trip, so it depends on different trip length and different time of the day. The price on the I-45 express lane will change. So those are the, again, dynamic, active strategy. All right. So where are our full ATM corridor? I mean, as I mentioned earlier, I-5 northbound. Why we're doing northbound only is because the southbound I-5 we have the reversible lane, so we can use that as one of the strategy to deal with the directional flow. Whereas on the northbound, we don't have the express lane facility or reversible facility, and we have to rely on this ATM strategy as well as the parallel route to help it. And the I-5, as I move the mouse here, and the project was actually part of the Alaskan Way tunnel replacement mitigation for the construction of that tunnel, and funding was coming out of that project at $23 million, and we have total 15 gantry spaced at half-mile apart. And then the year after that, we start the 520. The 520 ATM corridor, and it's about $20 million. Funding for that project is by the urban partner agreement, as well as I-90, same thing, about 11 mile long, $22 million from urban partner agreement funding. So what is the typical gantry sign layout? On the I-5, we have over one direction, but on the I-90 and 520, we have it across both lanes. And then sometimes we use the bridge overcrossing as a gantry. Typically, these gantry are spaced at a half-mile apart, and we base the half-mile spacing on the free flow speed of 60 miles per hour, and given the way we present the signing as when driver approach a closed lane, they will be warned by a by a merge arrow first, and that would give the driver approximately 30 seconds to look for a gap in the next lane to vacate that closed lane, and that's why we stick with the half-mile spacing for the gantry. Typical sign that we have for those ATM shown here, and they are actually graphic image, and they reside in the sign controller for the sake of quick deployment. So it resides locally at the controller and the memory slot, so that when the software for displaying this sign are actually developed in-house, so we can just poke into the right memory location. It will display really quick. And again, being a graphic image, we can make it very, very much like a static sign with the color and the rendition almost following as close to the MUTCD as possible. We had some minor tweak to this sign. Initially, we have the minimum speed of 35 miles per hour. However, after the first few months of deployment, the commuter feedback was that, well, sometimes the speed is stop and go, and they thought we should even go down to 30 miles per hour. So say, okay, we change to 30 miles per hour. So those are the small minor tweaks we had. And then also the yellow caution arrow is another tweak we had after we deployed the system for a while. It basically serves as a junction warning, and it is dynamic. It comes up when the RAM demand is high and the mainline volume is also high. It will come up as a warning over lane number 1, so arrival can vacate the lane. As you can see here, that the comprehension and understanding of message and compliance is pretty high. For example, under normal operating condition, such as kind of free flow a little bit, then nobody drive under the red X. However, when traffic is stop and go, and the red X being displayed usually is some distance upstream from the incident, and people would see an empty lane, and sometimes they will drive past the red X, but not at a high speed. I mean, again, they just gingerly drive under the red X, trying to find a gap in the adjacent lane to get out. The yellow caution arrow got a pretty good compliance also. It's not really compliant for yellow arrow, but people understand and follow the instruction quite well, especially along with those lane control signs. We have the VMS explaining the reason why that symbol is being displayed, so people understand and comply pretty well for the ATM sign we have in the area. The ATM deployment certainly increased our need for maintenance operation staffing. We had to add 3 more FTE to the TMC. TMC has been operating 24/7, but since the ATM is also extending into the after hour, we increased the night staff as well. And the VMS, the variable message sign inventory, all of a sudden increased from 70 signs to more than 350 signs in the region. So maintenance, we also add 2 more FTE and a boom truck to the funding there. And the other thing that we've done in the TMC is to reorganize the staffing in the TMC a little bit. Historically, the staffing at night in the TMC is more like maintenance, and their primary function has been dispatching or communication. Now they are into more flow management, because they are expected to deploy lane control, to override speed limits as needed. So there's a little bit of training there. However, the learning curve is pretty low. During the design of the software, we involve the operator, so they actually provide a lot of input to the user interface as well. Let me see. All right, so basically in the ATM system here, we have can be grouped into two separate how I say process. There's an automatic process running in the background, and it is the speed limit, the variable speed limit process is always running 24/7 in the background, and it only displays the lower speed when it detects traffic slowdown. In this case here, we're looking at approaching the downtown Seattle, where the queue is always forming somewhere in the downtown and then propagate as the time go on further upstream. And when there's an under pre-flow condition, the sign just go blank. And when traffic starts slowing down, then what the system did is that it detects the traffic flow downstream of the sign and display that lower speed just upstream. So it's kind of an advanced warning of the slow condition. And we find out that following this process, the driver follow the speed limit quite well, because as soon as they see the sign, within half a mile to a mile downstream, they actually encounter the condition that drive that sign limit. And then the junction warning is also another automatic process we're running in the background. As I show here, the yellow arrow with the message say heavy merging traffic ahead. When the RAM demand is heavy, and it pop up, and that process will override whatever the speed limit in that lane is showing. And there's also one thing I want to mention is there's a difference between the speed limit on the HOV lane and the adjacent lane. Here in Washington, we do allow HOV lane traffic to be driving at a different speed from the adjacent lane. In our software, we have to put a 15 miles per hour differential between the adjacent lane and the HOV lane, because the standard operating procedure for transit operator is that they limit their coach speed to 15 miles per hour under the adjacent lane. So let's talk a little bit about the yellow caution arrow. When we deploy this arrow here, we notice that the driver approaching this caution arrow actually, because it is dynamic, it is not on all the time. So when it is on, it catches driver attention and they vacate the lane. As you can see, lane number 1 is in the light blue color here. During the time when the RAM, on-RAM demand is the red line over here, is increasing, lane number 1 actually vacate the traffic approaching lane number on lane number 1 approaching the on-RAM is vacate that lane onto the adjacent lane, in this case here, on number 2. And what really helped us in this case is that the driver approaching the heavy merge condition realize there's heavy merge, and they prepare for the whatever evasive maneuver if they have to do to avoid collision. And by doing so, it appears they are willing to take shorter gap. And as we add the lane number 1 volume together with the on-ramp volume, we exceed the 2,000 vehicle per hour in that merge processing. So it's worked out quite well for us in merging warning. Okay, so let's quickly look at the scenario where we have an incident in the I-5 ATM corridor. In this case here, the operator received a call. There's an incident on I-5 blocking a lane, and we are monitoring the CAT system, and we saw it coming up. So immediately, you see on this user interface, actually at every gantry, there's lots of button or hotspot where there's a camera icon that they can bring the mouse to that camera icon, click on it, and immediately the camera will preset looking at the area around approaching that gantry, and we confirm location, confirm the number of lanes, which lane is being closed, and the operator is going to pull up the ATM user interface, and he will quickly put a red X over the lane that is being closed, being blocked. Then the next thing is they'll do the preview, and in the preview mode, immediately when these are the messages coming up around the only two, first he only needs to enter these two red X in the preview mode. The rest of the system filling in all of the, again, pre-canned messages, and these messages are the ones that I mentioned earlier, reside out in the controller so it can be quickly deployed. And once it confirmed that, yes, everything is clear, ready to go, next thing is, boom, hit deploy. Then again, the manual process in this case is the lane closer, the merge, and the adjacent through and all the messages override the background process, which has been speed limit process. And basically that's the software was developed in-house. So the whole thing was designed within 1 year, and the user interface and and the algorithm and everything was discussed in-house. So we're pretty happy with rolling out our own software. And here's what show in the field is closer and open next in field. Okay, and quickly mention about result. We get good compliance, and we for the speed as well as the lane control, and good result for the junction warning. In terms of accident improvement, we compare with similar facility around the area, and overall in the ATM corridor we have a reduction of accident, while the adjacent or surrounding arterial as well as freeway system have increased accident. So let's quickly talk about the next move after the full deployment of ATM. We have here is the hard shoulder running. The static one happened at the same time we are doing the ATM for I-5, and as a test case almost, it was static, open by time of the day, and we saw success on that static deployment. So we move on further onto the automatic or dynamic shoulder control, and in this case here we are looking at the I-45 along the express toll lane. Again, we capitalize on the success of our ATM software written in-house. So this is almost like an ATM Lite. So instead of having the gantry all across the lane here, we say, all right, we'll only manage the shoulder. Therefore, we'll use a very simple kind of a traffic signal, type 2 traffic signal with the sign over the shoulder. And in this case here, the spacing is also half mile, based again on the operating speed of 60 miles per hour. And we apply we develop the queue detection algorithm, or actually we enhance the queue detection algorithm from the previous ATM deployment, because in this case here we have the I-4 5 shoulder terminate at the I-5 shoulder. So, and then we also have a new process called the transition interval, going from open to close. In the ATM corridor, going from open to close is a simple red X deployment, whereas over here the transition from the entire facility being open going to close, then we have to go through a yellow interval. So the change will be like a temporal change. In this case, 30 seconds is where we will be transitioned from a green arrow to all merge arrow, then it go to all red. So those are the additional process we introduced to the previous ATM deployment. Apply here. And as a result, we see that the congestion, when we're looking at this congestion map, and the shoulder running is from Highway 527 onto I-5. That is the dynamic one. The static one is on the southbound, which is only open for transit. So let's talk about the one on the right here, northbound. The congestion map before the opening of shoulder lane, this congestion map corresponds to the area from 524 down to the 128 or Kirtland area. So as I move the mouse, this is the corresponding area of congestion we look at. So basically, after we open it, the area upstream from the shoulder is improving. So basically what happened is the shoulder release, the opening of the shoulder relieve the bottleneck here that help the upstream traffic approaching it. And a quick scenario of how this operates. You can see that in the first slide here, we have a disabled vehicle, and again, we use very similar process as we close the ATM on I-5. So we again declare a closure, segmental closure, by put a red X just upstream from the disabled vehicle, and the rest of the system automatically fill in. Downstream from this closure is the lane open up for traffic. And you can see that in the next scenario, the other scenario is the lane is currently open, and there's a disabled vehicle pulling into the emergency pull-out. Bev mentioned earlier that in the design, we got to consider emergency pull-out because we are taking the shoulder away from as emergency. So the way we design it, we have the pull-out adjacent or immediately next to the semi-gantry or the signal pole. And again, the reason is because this will serve as our maintenance pull-out as well as emergency pull-out, and it's kind of intuitive for driver to kind of gravitate toward that traffic control when they have to pull out. And again, the lane was not totally blocked, so we have the yellow caution arrow coming up alongside with it. So in the future, we probably will look more into this kind of ATM light. We probably will not be deploying a lot of full gantry across the roadway, only because the cost to maintain, traffic sign over live traffic is so expensive. We might have a few gantry in the existing corridor where we either extend the corridor a little bit, but otherwise we'll try to go with the ATM Lite, which means using the dynamic shoulder more. And we probably will try to as we go through with any resurfacing project, we'll try to see if we can rearrange the lane line from a 12-foot lane to a narrower lane, adjust the shoulder around so we can get a full wide shoulder on one side so we can deploy as a shoulder later on. And one thing I want to mention is that ATM alone will not be able to handle traffic in our corridor. So we, parallel with that ATM, we still have to work very closely with our partner for integrated corridor management. So what we're looking at is the I-5 ATM corridor, along with along with the integrated corridor management, where we have parallel route that during the off-peak hour, this parallel route really help I-5, especially when I-5 have some incident that we need to route traffic across onto the parallel route. And the pink circle you see over here are actually the what we call the network junction, is the interchange where traffic can vacate the freeway and get onto this parallel route. And again, when we message for people to change route, we target the user. So we can basically say downtown traffic or Seattle traffic, use early exit, especially when we have recurrent or non-recurrent congestion further downstream. And it worked out very well because I-5 peak period on I-5 is almost like a solid peak. From 6 in the morning until 6 in the PM, you have solid line of traffic, whereas all of the parallel route have a traditional morning and afternoon peak. So during the off-peak, there's capacity on the arterial first to send traffic over. All right, so where are we heading? We'll try to design for operation. We'll try to be practical. So the lane and the shoulder combination, we'll try to adjust the lane width, shoulder width, so that we can squeeze in a full shoulder should we need in the future. And then we also try to make our data station remitter ready, so we can just turn on, and for some additional money, we can make it as a remitter. And then in terms of Beverly mentioned about the inflow project, we actually have a pilot inflow project 2 years ago here in the same ATM corridor, where we send all of the ATM information second by second down to the server, so that the pilot vehicle can test it. And that project was done. I think Battelle is probably finalizing the report on that one. And the other thing is we want to continue the proven step that we had is always plan the seat for demand management, because there's no way we can build enough capacity. So we'll concentrate on the demand management and integrated corridor management. So with that, I'll turn this the slide to James for question and answer.
Okay, thanks, Ben. Great presentation and very robust systems you guys have in Washington State DOT, and some good practical lessons learned. So I saw a few questions come in, and we'll go through those quickly. I know we have a hard stop also at 3:30 p.m. Eastern, so we'll fire through these. There's a couple that came for you, Ben. So one of them was, do you have any instances on your ATM gantries where there's actually static signs also located on the ATM gantries that could not be avoided?
I don't remember having any static sign on the ATM gantry. We have some static sign in the shoulder where we say traffic is allowed in the shoulder only with the arrow, and that message is true whether or not the there's any ATM sign coming up. And we remove all of the static speed limit in the ATM corridor and replace it with the VSL, variable speed limit sign. And I forgot to mention that during the at-rest condition, we still have the VSL sign display the 60 miles per hour as the at-rest condition, and those locations of those signs are at a strategic location, such as around the major interchange, or entrance of a major ramp, following the requirement in the MPCD for placement of those at-rest signs. They are not static; they're changeable. And when there's a different speed, then those messages will be overridden by the overhead speed limit.
Okay, great. Thanks. Then it's always a challenge to fit in the full ATM system in a already established urban corridor here. So, good question. The other question for you then was, do you restrict heavy vehicles from using the shoulders?
Yes, we did. Vehicle on the 4.5, we restricted. We do not allow vehicle over 10,000 GWV in that. And again, not because of the structural integrity of the shoulder, but it's more for the width of the shoulder.
Okay, great. Couple quick questions that came in. One was on earlier slides, 39 and 40. There was a couple of screenshots of shoulder-mounted signs in Washington State DOT, and also the user interface for the ATM software. And the question was, can I get copies of those figures? And the answer is yes, you can. And a couple ways you can do that. One is the PDF will be made available, so you can do a screen grab from the PDF. Nilo is posting about how you can get the PDF of the presentation later. Another way is if you want a higher resolution figure, feel free to contact myself, James, or Vin, and we can maybe get you a JPEG or something. And then the last question about that was, who is the equipment supplier for the project, the ATM project? And I think it says DC, but I think the question is referring to the WashDOT project. And I believe the equipment vendor. Go ahead, Ben.
Yeah, I forgot the name of the vendor. They're European company. Also, the name escaped my mind, but it's an European company. Darn it.
Is that Telegra?
Telegra, yeah, Telegra. Yes. Yeah. Thank you, Jeff.
Okay, good, yeah. And contact Vin if you want more details about that. The last question was, is there a website for this project where I can get more information? And the answer to that is also yes. So just trying to advance the slide here. It's not letting me. Maybe Nilo, you can do that. There we go. Thank you. So here's the web link to the Federal Highway ATDM program. And when this ATM Implementation Operations Guide is published, it will be posted on the What's New section, and that's the web link right there. And that website also has a whole slew of resources on ATDM lessons learned, some informational briefs, the guidance document, other guidance documents we have, links to current and past research that we've conducted, and links to other publications such as videos, YouTube videos. Beverly talked about that earlier, public outreach that other state DOTs have done. So bookmark that web link or just Google FHWA ATDM, and there will be lots of resources there, including the one that we talked about today, the ATM Implementation Operations Guide. With that, here's a couple of points of contact if you have any other questions that you think of later. myself and Jim and Greg on the FHWA ATDM program team, Beverly from TTI, who you heard earlier, is the PI on this guidance document, and then Ben from Washington State DOT. So with that, let me just go ahead and thank everyone for attending. Let me also turn it over to Nilo for any closing wrap-up.
Thank you, James. I just want to again thank everyone for attending today's webinar, especially our panelists who had shared some good information with us today. Again, a recorded version of this webinar along with the presentation slides will be available on our website. And that's about it. So on behalf of National Operations Center of Excellence and our presenters, thank you again for joining us today, and have a great rest of your day. Thank you.
Thank you.